This is Mr. Goto with Anritsu. Today, I'm going to talk about Flit for the error correction analysis for PCIe Generation 6 receiver stress test. Thank you very much for attending this webinar. Today's agenda is, first I'm going to talk about overview of PCIe Generation 6. Then talk about what's new and what key of PCIe Gen 6. There are two new features of Gen 6. One is PAM4, the other one is for the error correction or Flit. Number 3 is PCIe Gen 6 for the error correction functions in details. Then new criteria of BER, bit error rate ratio, and fast BER and Flit errors. Then I'm going to talk about actual BER measurement and actual FBER measurement and Flit error analysis. There are 3 different measurement conditions for error measurement of actual PCIe Gen 6. Then error analysis and the relationship between Flit errors and fast BER, and consideration of the pattern dependency of these errors. Then conclusion, and at last, I would like to make a quick introduction of Anrit's bit error rate tester BERT of MP1900. First slide is key benefit of the PCIe Gen 6. The Gen 6 is a double the bandwidth, increase the data rate to 64 giga transfer speed. Compared to the last generation Gen 5, it's doubled, and providing a maximum bidirectional bandwidth of up to 256 gigabyte per second when you use 16 lanes. I don't know why, but PCIe SIG use sometimes bit, sometimes byte. So this generation 6 is 64 gigabit per second per lane. When you use 16, 64 times 16 will be like 1 terabits. But when you use byte, that will be 128 gigabit per second when you use 16 lane, and bidirectional 256 byte. So anyway, huge data bandwidth mainly for the data center, and it's like a new technology of AI. The concept of the Gen 6 is a low latency. Utilize flow control unit with fixed size, that is Flit, which allows the use of a lightweight forward error correction with pulse amplitude modulation PAM4. And also its strong cyclic redundancy check CRC. With these technologies, very low impact to the latency. Compared to the Reed Solomon of IEEE for the error correction, it's a very light for the error correction. I'm going to talk about the details in later. And the last one is the backward compatibility. In the last developers conference of PCIe, a lot of questions about the backward compatibility when we use like optical cable or jumper cable for new technology, PCIe Gen 6, Gen 7. But board members kept saying the backward compatibility is very, very important. So what's new? What key of PCIe Gen 6? The first one is a PAM4, pulse amplitude modulation. Up to Gen 5, Gen 1 to Gen 5, the modulation scheme was NRZ, no return 0, 1 or 0 digital signal. Gen 6 used PAM4, that is a 4-level modulation scheme. So in compared to NRZ, the PAM4 signal is 9 dB SNR reduction because it uses 4 levels. So automatically you lose 9 dB SNR. And also compared to the NRZ, now in the right side you can see the actual eye diagram. The eye opening of top eye and bottom eye is smaller than the center or middle eye, mainly because of the rising edge or falling edge. In general, the TRTF is 1/3 of the 1U eye. So when you use NRZ, the cross point is center. So the phase margin is almost 1U eye if the signal doesn't have jitter. However, when you use PAM4 modulation scheme, you can see the top eye and bottom eye margin is eaten by the rising edge and TRTF, actual speed of the rising and falling. You see the top eye, bottom eye, automatically the phase margin is reduced maybe by 20-30% because of the edge. To compensate this 9 dB loss and also smaller phase margin, further error correction is introduced to PCIe Gen 6. The merit of the PCIe Gen 6 FEC is strong CRC. So the concept of FEC is the burst error generated by DFE can be, oh, somebody change the slide. Okay, let me go back to slide now. Okay, so the DFE may generate a burst error, contiguous errors. The FEC, Flit FEC, may correct that burst error. Then CRC correct the random errors. So with the combination of this Flit FEC and CRC, the PCIe guarantees a robust communication. Then PCIe Gen 6 FEC function details. The one flit consists of 256 FEC symbols, and one FEC symbol consists of 4 PAM4 symbols. One PAM4 symbol consists of 2 bits, well, which means one FEC symbol consists of 4 PAM4 symbol, that is 8 bit. So 1 byte is 1 FEC symbol. And again, the one flit consists of 256, which means one flit consists of almost 2,000 bits. Then 1 byte error can be corrected, or 2 contiguous byte errors, that will be 16 bits, can be corrected by FEC. When you use single RAM, that is a criteria of FEC card target. When you use multi-RAMs, like by 2, by 4, by 8, by 16, that kind of burst error can be distributed. So the FEC can be easily fix the problem when you use multi-RAMs. but the target of guard is same. So this is the detail of FEC. The data of Flit are interleaved into 3 groups per 1 byte or 1 FEC symbols. So they call it 3-color FEC scheme. And forward error correction can correct a burst error in 1 Flit and a contiguous 3-byte error, assuming 2-byte error doesn't occur in the same group. As I said, PCIe SIG believes that kind of burst error will be generated by DFE of the receivers. So up to 3-byte error, that will be 24-bit contiguous error, can be corrected by FEC. When 2-byte error in the same group in 1 Flit is occurred, it is uncorrectable. And in that case, CRC works to resend the packet, sending a request of not acknowledge and resend or retry or replay. That is the mechanism of FEC. So now you can see the example of Flit errors. So in a blue Flit, no errors, but in a red Flit, it has errors. And you can see the inside of the Flit, there are 3 colors: blue, orange, green. One error in 1 FEC symbol is just 1 FEC symbol error, regardless the numbers of the bit error in 1 symbol. If you 1 bit error, 1 symbol error, even all 8-bit errors, that is just 1 symbol error. Then contiguous 3-byte errors of FEC symbol can be corrected by FEC. But in this case, you can find orange, 2 orange has FEC symbol errors. In that case, that error cannot be corrected. That will be Flit errors. And there's a definition of Flit error rate. That will be uncorrectable Flit divided by total Flit. That is equal to the retry rate. So the criteria of the BER and FBER and fail path and Flit errors. FBER, the definition of the FBER is successive burst error propagating by DFE will be counted as a single error. So if you have like 3, 4, 5, 6 contiguous errors, that will be a group of 1 just error. And first BER is defined as like a raw BER, it measures every single bit. But FBER, the concept is when you have contiguous error, that is just 1 error. So the new criteria, the target value of the physical layer FBER is E-6, assuming for the error correction is used. So compared to the generation 5 or previous generation, PCIe SIG always use E-12. So it's almost no errors. But now PCIe Gen 6, because of the PAM4 and loss of the channel, it's going to be very difficult to get error-free. So that is because for the error correction is used, and the new criteria is E-6. Then that FBER E-6 is decided based on the assumption that the retry rate must be 3 times E-5 to have very stable communications. So the retry rate cannot be measured easily, but fast BER can be measured. So that E-6 is selected based on the fact that retry rate must be 3 times E-5. That is the definition. Just for your reference, you can see two different pass-fail criteria on the bit error rate testers. PCIe Gen 5, 1 error or 0 error pass, 2 or more than 2 errors is fail for Gen 5 125 seconds. So confidence level of E-12 is like a 90% or 95%. PCIe Gen 6 is completely different. The fast BER E-6. The good thing is PCIe Gen 5, Gen 4, to have a good confidence level, like a 90%, 95%, the measurement time is quite long to have a good confidence level. PCIe Gen 6, E-6, so it's immediately you can tell that is fail or pass. Okay, so that is the kind of a theoretical basic fundamental. So next, I need to measure the actual fast BER and BER and uncorrectable flit errors. So let's go to the actual data. This is the block diagram of this actual measurement. And its MP1900A is the bit error rate tester. It can generate a signal and a compliance pattern or any pseudo-random pattern, PRBS pattern. It goes to a PCIe Gen 5 base CBB, so ISI board. And it goes to the Gen 6 clock data recovery. So this is the DUT. And through the DUT, the signal go back to the error detector of and it's 1900 parts. First measurement is loss versus FBER. So change the loss value to 4, 8, 12 inch, 16, 20, 24 inch. And this PCIe Gen 5 baseboard has almost 1 dB per inch. So this 4, 8, 12, 16, 20, 24 inch means 4 dB, 8 dB, 12, 16, 20, 24 dB loss at the Nyquist of 16 gigahertz. Then all stress is off. No SSC, no sinusoidal jitter, no RJ, no DMI, no CMI. Everything is off. And launch amplitude of the pulse pattern generator is 800 millivolt peak-to-peak differential. And optimize the TX equalization or preset DUT equalization to get the best BER. And test pattern NOP flit by 1 is used, so 1 lane. And this is the test result. The blue line is PAM4 symbol error rate, and yellow is fast BER. Then green is flit error rate, so it is almost the same as the retry rate. Up to 8 dB loss or 8 inch loss, all three no errors. But 8 dB, you start seeing some symbol PAM for symbol errors. Then also you can see fast BER, almost 10 minus 10th. But they are all correctable. So, but reported. All errors are corrected by FEC, so no Flit errors. 16 dB, same thing. But when the loss is at 20 dB, now the low BER is E minus 7, and fast BER is also almost E minus 7. In that case, retry rate or Flit error rate is E minus 8. So the spec of fast BER is E minus 6. Then when the FBER is minus 6 or better, now the retry rate is less than 3E minus 5. So it verified the fast BER can be used to judge whether or not retry rate doesn't exceed the criteria of 3E minus 5. Then next measurement is the SJ or jitter tolerance. So use 12-inch of PCIe Gen 5 again. So 12-inch means here the fast BER is almost 10 E minus 10th, 12-inch. Then RJ, DM, CM, SSC is off, but SJ is a knob to see the FBER and not correctable Flit errors. So change the SJ 0 to 160 milliui. Same TX launch amplitude, and again it optimizes the equalization preset and PFE on the error detector side. Same data pattern. So it starts almost minus 10 E minus 10 BER when the SJ is 0. Inject the SJ, increase the SJ by 20 milliui, and up to 80 milliui or 0.08 UI SJ, no Flit error is detected. The BER, fast BER and low BER is increasing linearly like this, but up to 80 milliui SJ injection, all error can be corrected. However, 100 milliui SJ injection, now some errors cannot be corrected by FEC, that becomes Flit errors. Then when the FBER is almost E minus 6, still retry rate or Flit error rate is less than 3E minus 5. So this also verify the FBER E minus 6 can be used. Then when the injection is 160 milliui, the FBER exceeds E minus 6, so that is failed. And also it shows the Flit error rate or recent retry rate is exceed 3E minus 5. So it also verify when the fast BER is worse than E minus 6, that doesn't guarantee the stable communication because the retry rate is worse than 3E minus 5. Then last measurement is the almost same condition, but it is under the compliance test. It's still a draft of receiver compliance test. So this is a kind of a nominal numbers using 12-inch PCIe 5 base ISI, that is almost 12 dB loss. Inject SSC 5000 ppm. Inject RJ 0.25 picosecond RMS, that is almost 150 milli peak to peak. And DMI, differential mode noise, vertical noise at 2.5 gigahertz, 15 millivolt, and CMI 75 millivolt, 120, not gigahertz, sorry, it's megahertz, it's typo. And SJ is again knob from 0 to 100 milli UI. Same launch amplitude 800 millivolts, always equalization, then NOP Flit pattern. The test result is the all three PER is like a kind of correspondent, and up to here 80 milli UI, the first BER is almost E-6, then still retry rate is less than 3E-5. So even the compliance conditions, the first BER can be used to make a judgment of retry rate less than 3E-5. So this is a really convinced data to use first BER. Okay, so now the analyze of the data in details. So the measurement condition 12-inch 100 megahertz conditions, and in this case we found FBER, first BER is 8E-8. Also raw ROW, raw BER was 8.23 E-8. So that means FBER and raw BER is exactly same, which means no burst error is happened, mainly because this is a DFE only one tap, and also CDR is kind of a passive, so no burst error happened. The errors are all random error and some are pattern dependent errors, but not created by DFE. And you can find the MSB error and LSB error. MSB error is almost 10 minus 10th, and LSB error is 10 minus 7. This is a very typical conditions or phenomenon. The MSB most significant bit that goes to the middle eye. So middle eye is always the biggest eye, and phase merge is biggest. So the BER of MSB is always better than LSB error. LSB error, least significant bit error, is top eye and bottom eye. And you can see 2 or 3 decades worse than the MSB, but this is very typical. And then when the error detector analyzes when error happens, the error detector finds when the symbol change 0 to 1, the almost error happens. 95% errors happens when the symbol moves to 0 to 1. So this is the kind of a function of its error detector to analyze what's happening when the DUT generates errors. Next one are same conditions, but inject SJ 800 milli. Then now FBERs and Flit error rate is different, which means some burst error happened. But actually, you can find the error rate of FBER is E minus 8, 6.83. Flit error rate is 7.8. So, which means in one flit, there's a 2 ECC error happens. So that means a flit error ratio is worse than the actual FBER. So this table shows the relationship between flit error rate and FBER. And the blue portion, FBER, the top one, 8 E minus 8. In that case, flit error rate is 7 E minus 9. So good. But when the FBER is E minus 5, then flit error rate is E minus 4. That means FBER can be used to judge the retry rate of flit. So we confirmed FBER can be used. In any case of loss, SJ and compliance test, FBER can be used to judge the flit error rate or retry rate can be less than 3 E minus 5. Then the error detector has a capture function, and it just captures when the burst error or uncorrectable flit error happens. So it can be triggered when the error detector detects any uncorrectable flit errors. And in this case, you found 2 errors happened. And blue is ECC 0 and yellow is ECC 1. So 2 same color errors happened. That is uncorrectable flit. And we found always happened 0 to 1. That means expected 0, 2, but error detector 0, 1. That's yellow portion. Or 3 to 1. Expected value 3, 0, but error detector detect 3, 1. So you can find 2. So that kind of capture data tells you which kind of data stream may cause the error on your DUT. So conclusion, and it's confirmed that FBER and flit error meet the standard values based on the reasonable actual measurement. And for in the future, and it is going to make another measurement of burst error, which can be generated by DFE. In this case, kind of a random error or pattern-dependent errors, but in the future, this is going to test errors caused by DFEs. Thank you very much. Then let me make a quick introduction of and its part, MP 1900. You can see the picture. This is a plug-in, configurable and expandable bit error rate testers. It is multi-channel PAM4, NRZ, and also PAM3, but from 2.4 up to 128 gigabit per second per lens. And you can configure up to 16 lanes of NRZ or 4 lanes, 4 channels of 116 gigabit per second PAM4. It is a PCIe, USB, Thunderbolt link training, and equalization, and LTSSM analysis, so protocol aware. It supports 3 clock architectures, common clock, separate ref clock, with and without SSCs. The signal integrity of the PPG is a great advantage, very low intrinsic jitter, very fast TRTF. And error detector side, 12 dB CTLE. The PPG side, it has maximum 10 tap emphasis, and each tap can be adjusted plus minus 20 dB independently. The jitter injection, 2 different SJ, sinusoidal jitter up to 250 megahertz, random jitter, BUJ to simulate crosstalk, half-period jitter, and SSC injection. Particle noise, you can inject CM, common mode noise, DM, differential mode noise, and broadband white noise injections. So we support PCIe Gen 1 to Gen 6, Thunderbolt 3, USB 3.1, 3.2, and 4.0. IEEE 100, 200, 400G Ethernet, InfiniBand, and optical mutual service test. And the last slide, and it is contributing these standard, and MP1900 is a approved golden test suite in PCIe Gen 3, Gen 4, and Gen 5, and now making a proposal for Gen 6.